Hi, my name is Lillian Petersen, and my project was America's Farming Future, the impact of climate change on crop yields. My question was, how will various future climate scenarios affect the future crop yields of corn, soybeans, and rice? And I hypothesized that because crop yields are dependent on weather, more heat extremes will cause future crop yields to decrease. In order to test my hypothesis, I had to create something that could accurately predict crop yields in the US based on weather. So I created a statistical model that found correlations between past yields and weather. This model was used to predict yields out to the future. In order to create this model, I wrote 3,500 lines of my own Python computer code, which took me 6 months to develop, and I also used 207 gigabytes of data. First, I downloaded seasonal crop yield data for every county in the US and year since 1970. This data was from the USDA. 1970 was chosen as a start date because, before then, crop yields are more variable and farming practices were less standardized. This plot shows the corn yield over time for a single county of 1,042 corn-growing counties. The yield has increased since 1970 due to improvements in agricultural technology, such as irrigation, pesticides, herbicides, fertilizers, and plant breeding. However, the yield year to year depends on the weather. So next, I downloaded daily weather station data from the Global Historical Climatology Network for every weather station with data since 1970. Next, I averaged the two closest weather stations to the center of every county, so I could find the correlations between yields and weather. This plot shows for that same single county, the summer average temperature plotted with the corn yield detrended. When there is a very high summer average temperature, the corn yield for that year is very low. I found correlations between yields and over 20 different temperature measurements, shown here. And the ones with the highest correlations were summer average temperature, heat waves, and killing degree days. Summer average temperature is the average temperature over the months June, July, and August. A heat wave is 3 days in a row above the 90th percentile for that county, and killing degree days are the number of degrees and days over 68 degrees Fahrenheit. So what I did for this plot here is I took the summer average temperature and corn yield for a single year and plotted it as a single dot on this plot. Next, I fit a best fit line and found a correlation. In order to get correlations such as these, I first had to detrend the yield due to the technology increase. This is a standard thing to do in this field, because if the yield wasn't detrended, then the correlation would be higher with the year instead of with the weather. The correlations for this single county are -0.71, -0.71, and -0.67, and they are all considered highly significant. Next, I repeated this process for every county in the US. These plots show the correlations. Every county that is red means there is a significant correlation, and every county that is dark red means there is a highly significant correlation. These plots show the slopes of the best fit lines. Almost all the slopes are negative, meaning when there are higher temperatures, there are lower yields. The counties in the south are very negative, meaning when there are higher temperatures, there are much lower yields. However, in the north, the slopes are either at about zero or slightly positive. This means that the yields aren't dependent that much on temperature, and it implies that, in the future, the places where crops are grown will most likely shift north to places with naturally colder temperatures. I then repeated this process for soybeans and rice. These plots show the correlations between the crop and heat waves. Corn has the highest correlations, with an average correlation of -0.46. Soybeans is slightly less, and rice is much lower. Now that I had my statistical model comprised of correlations and slopes of the best fit lines, I could now predict yields into the future. So I downloaded future climate model data out until year 2100 for two scenarios, low emissions and high emissions. The data came from the Coupled Model Intercomparison Project version 5, or CMIP 5, and came in high resolutions in space, 1/10 of a degree, and time, daily. Next, I found the closest model grid to the center of every county, and I found my temperature measurements out until year 2100. These plots show the temperature measurements over time, from 1970 to 1980, 2090 to 2100 low emissions, and 2090 to 2100 high emissions. The historical summer average temperature was at about 85 degrees Fahrenheit. Future for low emissions is at about 91 degrees, and future for high emissions is at about 97 degrees Fahrenheit. The results are similar for the other two temperature measurements. All models include assumptions. Some of my assumptions are that temperature has a larger influence on crop yields than other factors, such as precipitation or soil conditions. And I tested my model with precipitation, and I found little to no correlations with yields. I also assumed that as the temperature increased, the slope of the best fit line would continue past the data. biggest question in this project is whether technology will continue to improve in the future and at what rate it will continue to improve at. So I plotted the two extremes, where technology stops improving today and where technology continues to improve at exactly the same rate as it has been since 1970. However, even with this scenario, there is a huge loss in yields. For corn, by year 2100, for a low emission scenario, there is a loss of $17 billion per year. And for a high emission scenario, there is a loss of $23 billion per year. Because corn had the highest correlations, it is affected the most by heat extremes, and is predicted to decrease the most in the next century. Soybeans will decrease slightly less, and rice the least. This is likely due to differences in the plant's biological structures. Corn and soybeans are both C3 plants, and rice is a C4 plant. C4 plants minimize photorespiration, making them less susceptible to heat extremes. This is most likely why its correlations are so low, and it is predicted to decrease so much less in the future. In conclusion, I created a statistical model in order to predict yields into the future for 3 crops, corn, soybeans, and rice, and 2 different future climate scenarios, low emissions and high emissions. With my model, I show that crop yields are dependent on temperature. The geographical distributions of where crops are grown will most likely shift north in order to compensate for warming temperatures. We should also develop farming practices and crop breeds that are more resistant to stronger and more frequent heat extremes. This project predicts crop yields in a dollar amount, and such projections provide a convincing argument to reduce fossil fuel usage today and continue to support agricultural technology improvements. And this is part of a cost-benefit analysis. The total of these future costs should be compared to the cost of reducing greenhouse gas emissions through energy efficiency and renewable energy sources.